Hi everyone, welcome back to Power Electronics session 4. I hope you are good with the previous videos and looking at those and then getting the concepts. With the previous videos, I can conclude we completed the rectifiers including the source and inductance circuit. Now we will discuss about the next chapter, that is about commutation of the thyristors. Again, I am reiterating, if you are having any questions and all, so you can put in the comments there, or otherwise you can mail me through this ID and then we can discuss that. We can discuss about your questions. Okay. Then, commutation of the thyristors. What is the meaning of the commutation of thyristors? What we discussed, general commutation is nothing but it is the changing the current path one to another and all. Same way here also, but how we will actually change the current path from one to another is actually important in case of commutation of the thyristors. But in general, the commutation of the thyristor is nothing but it is the turning off process of the thyristor. Turning off process of the thyristor is called as commutation. As we discussed in the first class, we can only turn off the thyristors by using one and only method. What is that? Okay, let me explain. Thyristor can be turned off by reducing the anode current below the holding current. That's what we discussed in the fundamentals of the thyristor. But how you will bring this anode current below the holding current is important. That depends on which type of commutation method you are using. Okay, so we'll discuss further. So now we will look at that, what type of commutation methods are there and what are the commutation classifications are there, and then we'll discuss about some important circuits. So if you look at that, generally commutation will be classified into two groups. One is natural commutation another one is forced commutation. Okay. Natural commutation and forced commutation. If you look at a natural commutation is nothing but it will happen without any external circuitry. That means for the commutation of the thyristor, no need to have anything or any extra circuit to do that. So that's the meaning of natural commutation. That is why we haven't discussed anything separately in case of rectifiers, because in case of rectifiers we'll have the natural commutation. Okay, so natural commutation will happen if you have a AC source. That means natural commutation is possible in only few cases, that is nothing but rectifiers, AC voltage regulators, and requires AC source. Without AC source it won't be possible. That means why it is happening with AC source means AC source will have the natural zero current, natural zero crossing property. That means if you take it as like a sine wave as an input, that means in rectifiers we use the sine wave. So in case of AC sine wave, current will actually cross the zero at 180, 360 and so on. That means for every 180 degrees current will cross the zero. As soon as the source current comes to zero or source voltage, if the source voltage comes to zero, at that time Thyristor current, nothing but load current, because the load current is only flowing through the thyristor. That will try to cross the zero axis at that point if the load is resistive. If it is the inductive load, then it will cross the zero after that point, but anyway that current has to come to the zero. Whenever this current comes to zero, then thyristor will be turned off because that anode current is below the holding current. That is why natural commutation is possible in case of rectifiers, AC voltage regulators, step-down cycle converters. Here, step-down cycle converter is nothing but output frequency is lesser than the input frequency. That's the meaning of step-down. Okay. So, but now, like in other circuits, like inverters, DC to DC converters, or step-up cycle converters, source is not AC. Okay, especially DC to DC converters and inverters. Cyclo converters is a different story for the step up. Don't worry, even the AC, we need to turn off the thyristors at some current which is more than the holding current. That's why it is actually not possible now. So for now, no need to worry, we'll discuss later on. So force commutation requires some extra circuitry to reduce this anode current below the holding current. That is why it is called as a force commutation. This force commutation will happen in inverters, DC to DC converters, or DC choppers. Then step up cycle converters. Okay, cycle converters, step up cycle converters, DC to DC converters, and inverters. But remember, to turn off these thyristors used in these circuits, we require extra arrangement. That extra arrangement is called as a commutation circuit. That is what we are going to discuss about. Okay. So again, I'm just telling that natural commutation is possible only with AC. Other than AC sources, we need to go for commutation circuit. Okay. So to turn on the conducting thyristor, we require some circuitry, that is nothing but commutation circuit. In that also, especially we require capacitor, inductor, and sometimes additional thyristor to turn on the conducting thyristor. That means most of the times you will have circuit elements in particular commutation circuit will be inductor and capacitor. Both are actually very important, and auxiliary thyristor, which is required to turn on the conducting thyristor. Okay, so these are the main things. So here generally we have two types of commutation circuits, commutation methods, I can say. Two types of commutation methods again is nothing but, I'm again telling that this is in the forced commutation only. So two types of that. What are the two types? One is like a voltage commutation method. Voltage commutation method. And then other one is current commutation method. Okay, so what are these voltage commutation and current commutation method? We'll discuss with a little bit with the help of examples. We'll discuss about what is this voltage commutation method and current commutation method with the help of examples, small circuits. So here, assume you have some circuit with conducting thyristor like this. So assume this is some 100 volts and this having a load of maybe 5 ohm resistance, then it is actually drawing a current of 20 ampere. Okay, so that means this thyristor is in conduction, and then it is actually constantly, always it is drawing the 20 ampere current. So that means this current never come to zero, because this source voltage is 100 volts, that and resistance is constant. That means this never be zero. That means thyristor current. Then in that case, how will you turn off this stuff? In case of AC source, then this voltage will actually reach the maximum, then again coming back to zero. In that case, you can actually in case of AC source, this voltage will actually reach the maximum and then slowly back to zero. At the time of zero, this load current will also be zero, and then thyristor current will be zero. That time, this thyristor will be turned off. But in case of DC source, that won't happen, because this is constant voltage, then constant load, that current will be constant. So to do this, we require the commutation circuit. In case of voltage commutation circuit, we need to, we generally, like I'm telling the principle. So in general, what we do, that means for this conducting thyristor, we will apply sudden reverse voltage. So once you apply the sudden reverse voltage, then what will happen? This thyristor, conducting thyristor, suddenly become reverse biased thyristor. Okay, generally in electrical circuits, if you have like this is a 1 volt or this is 100 volts, doesn't matter. Okay, so why it doesn't matter means the voltage source or voltage is suddenly subject to the device across that will have more impact than the source voltage, because this is directly impacting that. Even though this is the 1000 volts, this is 1 volt, doesn't matter, this thyristor is reverse biased. So that is what actually here we are discussing. So that means if you suddenly apply the reverse voltage, then this thyristor will be reverse biased and it will be turned off immediately. So that is the concept of voltage commutation circuit. Okay, how this voltage commutation circuit generally we will do that analysis. In general, we will assume that this is the thyristor, and we will have a commutation circuit more or less with the help of capacitor. We will have because charged capacitor can act as a voltage source. Okay, so we will charge the capacitor like this, and this mechanical switch, or it can be anything. Okay, this is a mechanical switch is there, assume here it will be open now, and this thyristor is actually conducting or carrying a current of some current like this. So it will be open when you want this thyristor to be in conduction. In case you want to turn off this thyristor, then we will actually close this switch, and then you can see that this capacitor suddenly appear across the conducting thyristor in reverse biased. That means we will applying the impulse voltage, sudden voltage to the conducting thyristor in reverse direction. That's where you will have the voltage commutation. So to do this voltage commutation, we will have a different circuitry, and how we will charge the capacitor, all these things we will discuss later. But this is the fundamental concept of the voltage commutation circuit. Next, move on to the current commutation circuit. So current commutation circuit means same way. We'll assume that we can take the same circuit. Okay. So as we assume that this is actually having 100 volts, and this is a 5 ampere, and this is like a kind of carrying a current of 20 ampere always. So 5 ohm and 20 ampere always it is carrying. Now how will you turn on this conducting thyristor, because it is always carrying a 20 ampere. So in that case, what we assume that here we will actually give the sudden reverse current. Okay, so we will apply the sudden reverse current to the conducting thyristor. That means here, if you actually connected this current source like this, means this will supply the current like this. So as soon as, maybe assume that if you want to turn off this thyristor using the current commutation method, this current must be more than the conducting current or carrying anode current of the thyristor. Otherwise it won't be turn off. That means we will apply the reverse current to the conducting thyristor. Then it is like a kind of 21 ampere means, assume, for example, I'm telling that. What will happen? Resultant will be 1 ampere in the reverse direction. 1 ampere in the reverse direction. So that means this thyristor won't conduct in the reverse direction. And whenever you are actually changing from positive to negative, it has to cross the zero. That means before coming to the negative current, this current will come to the zero through the thyristor T. Then obviously this thyristor will be turned off at that time. So that means here we will use the reverse current for the commutation circuit, current commutation circuit. That's the meaning of that. How we will actually do this in the real circuit or real scenario, commutation scenario, means we will do the same way. That means we will have that thyristor. But in case of voltage commutation, we assume that a kind of like a voltage source will be given, but here current source means inductor will be there. So inductor, if you actually, you know that charged inductor can act as a current source. So whenever you want, once this inductor is charged like this, then if you close this one, means this will start supplying the current like this. So this is a current source. So with this I am stopping here. Then we will discuss the rest of the things in the coming videos. Thank you. And as I told you that, please subscribe to the channel, and then you will get the notification whenever the new video is added. Okay, thank you so much, and we will meet in the next session.